Hello, people, and welcome back to another session. In this session, we'll be looking over the concept of regression diagnostics. Why regression diagnostics are important? Well, regression diagnostics are important because before we actually go and perform statistical inferencing in our regression models, we actually assume a few things about the model. And if these assumptions are valid, only then the statistical inferencing or the conclusions that we draw from statistical inferencing can be kept sacrosanct or they are actually true. Otherwise, if any of these assumptions are invalid or do not hold true for that model, then whatever conclusion that we will draw from our statistical inferencing, that that will not be an accurate conclusion. Therefore, before we go and perform statistical inferencing on our regression models, we need to make sure that these assumptions or these assumptions of regression diagnostics are valid for our model. These regression diagnostics are performed for both simple linear regression and multiple linear regression model. So we will look at each of these assumptions, but first let us discuss residual plots and a few minor concepts that you will need when you will be studying about the four assumptions. But primarily, what you need to understand is what residual plots are. So basically, if you have a scatter plot that tells you about the association between a dependent variable y and an independent variable x, and the points are distributed like this. I'm drawing some random points. So now we suppose that there is a regression line like this. This is the regression line that we get from our simple linear regression model that fits these points most accurately. Now, what residual plots does, or what residual plots is used for, is to basically measure the error of prediction. So we already studied about the least square error or the least square regression error, which is basically the difference between the actual value of a point and its predicted value on the regression line. So residual plots are very similar to your scatter plots. What residual plot does is that it shifts your regression line parallel to x-axis. Let me repeat myself. It shifts your regression line and makes it parallel to the x-axis so that your measurement of errors of all the given points in the dataset becomes much easier, because then you will be able to see the perpendicular distance much more clearly when your line is parallel to the x-axis. So let us draw. So this is my scatter plot. Let me draw its corresponding residual plot. So again, let me tell you a caveat. It will not look accurate, but we got to do what we got to do. So let me just quickly go ahead and draw the residual plot. So it will be something like this. Now here, as you can see, the my ability to see the perpendicular distance or the error of this point becomes much more easier, because now I know this is the perpendicular distance, and this perpendicular distance will be same as that we will see here. So it's basically taking this particular line and all the points on that and basically rotating that until my line becomes horizontal. And once my line becomes horizontal, I can see the perpendicular distances more clearly. So this is what a basic residual plot is. So this is my residual plot. Now there are two important concepts out here, the concepts of outliers and influence points. Now outliers are something that we have already seen. Basically, they are points that lie beyond the extremities of the box plot. The extremities of the box plot are given by the first quartile minus 1.5 into interquartile range, and the third quartile plus 1.5 into the interquartile range. So if I have to show the outliers on a residual plot, there can be two types of outliers. When I say two types of outliers, it means that what I'm what I'm actually trying to say is that on a residual plot, when we show outliers, or when outliers are basically when outliers are identified, then they can be either identified on the extreme x end or the extreme y end. Let me show that with an example. So if this is my regular concentration of points for this residual plot, and all the points lie here, I'll remove this and I'll just extend this line. We'll go with more points. There is a point here and there is a point here. Both of these points are technically outliers because they lie separate from the rest of the points. But if you see this outlier right here, this is an outlier in the x direction, and this outlier right here, this is an outlier in the y direction. Okay. Now, the property of an outlier in the y direction is that an outlier in the y direction, they have large residuals, which you can clearly see over here, because this is basically the distance that this particular point has from the regression line, and compared to all other points, it has a greater distance. So these points, they tend to have extremely large values of your residuals. So this is one thing, and the other thing is outliers in the y direction tend to become influence points. Now what this means is that if you look at your outliers on which are far along the x, now what they have a unique tendency. They have a tendency to pull the regression line towards themselves. Okay, let me repeat myself. Outliers which are along the x direction, they have the tendency to pull the regression line towards themselves, which is why what becomes really very important is that you cannot directly remove an outlier which is in the x direction. You need to remove that point, check the impact that it has on the regression line. Only then, if it does not have a significant impact, only then you can remove it. Unlike the outlier in the y direction, which you can directly eliminate, an outlier in the x direction must be checked for its influence on the regression line, because it has a tendency to pull the regression line towards itself. So let me once again reiterate, an outlier in the y direction tend to have large residual values, and in majority of the cases, they can be eliminated right at the onset. However, an outlier in the x direction, they have a tendency to pull the regression line towards themselves, therefore they cannot be directly eliminated. We must remove that outlier, check the impact of removing that point on the regression line, and finally take a decision whether we want to remove it or not. Okay. So now finally that we have gone over a brief discussion on residual plots, let us go over and check the four principal assumptions of regression. Now there are four basic assumptions that we need to check for, and all four of them must be valid for our regression model. Otherwise, as stated right at the onset, our any conclusion that we will draw from our statistical inferencing will be erroneous if any one or more of these assumptions are not valid for our model. So let us go ahead and check what these assumptions are. So my first assumption is my assumption of linearity. My assumption of linearity states that between my dependent and my independent variables, the association between them must be linear. That is the first assumption. That the linearity assumption states that there must be a linear assumption between my dependent variable and my independent variable. Now, there are a couple of scenarios where you'll you'll see violation of this particular linearity assumption. Specifically, we can check this assumption using a residual plot. So let us suppose that I have something like this, and there is a regression line that fits like this. Now, an easy way to check my linearity assumption is through residual plots. Now, if I plot my residual plot for this particular scatter plot, I'll get something like this. Okay, it's going to be something like this where you can see a non-linear pattern in the points with respect to my regression line. There are other scenarios of violation as well, and all these scenarios have one thing in common, that the distribution of points with respect to the regression line is non-linear. It can be something like this, or this is my kind of a pattern that is being formed, or it can be something like this, basically kind of a sine wave. So any pattern that is non-linear in nature violates the linearity assumption for a regression model. This is the first principal assumption of regression. The second principal assumption of regression is that the observations that we are choosing, they have to be independent. It means that if there are more than one independent variable, then the way these independent variables are sampled, they have to be randomly sampled, and therefore there has to be independence between the explanatory variables or my samples. That is the second assumption. The third assumption is the assumption of constant variance. Let me just expand this a bit. Constant variance around the regression line. So what we ideally want when it comes to constant variance is that we want our points to be randomly scattered around the regression line, and there should not be a change in variance from one end of the regression line to the other end. This is also something that we can check from our residual plots. So ideally what we want if this is my regression line on a residual plot, I want my points to be randomly scattered like this. Both on top and on bottom, I want a random scattering of points. A situation like this, it is in sync with my assumption of constant variance. Now, what are the examples where my points are not in sync with my assumption of constant variance? Let us go over a few violation scenarios. There can be a scenario where the variation out here is very high, and as you go forward or as you move forward, the variation keeps on decreasing. Something like this. Or the opposite case where the variation is less over here and it goes on increasing. These are some of the scenarios where the assumption of constant variation is violated. Ideally, we want a scenario like this where the distribution of point around my regression line is randomly distributed. And the final assumption is the residuals have to be normally distributed. This is pretty straightforward. Basically, it means that my residuals of my actual values, which is my actual values subtracted from my predicted values, if I draw a distribution of that, that has to be normally distributed. Okay. Now, before I move forward, let us go ahead and let us look at an example of how we can perform all of these tests in R. We'll go back to the example where we had the relationship between exam score and hours of study. I will create a model and I'll draw a regression line, something like this. Now for this, if I have to basically, basically if I have to draw a residual plot for my residual and along the hours of study. So what I'll do is that I'll make a plot between my residual value of the model and hours, and to represent the regression line horizontally, I'll plot the AB line like this. So now you can clearly see this point right here. This can act as this is basically an outlier along y direction. I don't see any particular outlier along the x direction because of the kind of distribution that is there. So I only see one outlier here along the y direction. If you look at the points are randomly scattered. And because they are randomly scattered, we can say that the assumption of constant variance is valid over here. Also, what we can see here is that there is no non-linear relationship between the points. And because the points are evenly distributed up and down, we can say that the assumption of linearity is also true for this particular scenario. To check my final assumption, what I'll do, I'll just make a histogram for my residual values of the model. The histogram looks something like this. So more or less, if you will see, it is normally distributed with no heavy skewing on either side. So for this particular model of mine, all four assumptions are valid. And because all four assumptions are valid, we can say that my statistical inferencing that I'll draw from this model will be accurate. Okay. So this was the basic concept that I wanted to cover in this session. Let us go over a few basic definitions or some of the other basic concepts. First is the concept of extrapolation. Now, these are some of the nuances around simple linear regression and multiple linear regression that we'll be studying. Very easy concepts, not very difficult to understand. Extrapolation is application of regression model outside of the given range. An example of that is that if there is a model and that model can only be applied to data of a given range. Let us say that I have a model and I want to apply it for students of ages between 20 and 25. But if I apply that model on on a student whose age is 29, then that is a violation on that model, and it is a violation of extrapolation. I'm taking my model, which was between 20 and 25, I'm extrapolating that and I'm applying it to another student who does not fit in that range. That causes the problem of extrapolation. The next concept is of a lurking variable. Now, lurking variables are basically variables that are not taken into consideration when we are building the model, but they are hidden variables that might have an impact on the dependent or independent variables. A very good example of that is that when we talked about our CEO salary example, then we saw that the independent variables were height and age, and those were having an impact on salary. But there can be also an important factor of skill set, let's just say, which we haven't taken into consideration, but that might have a significant impact on the dependent variable salary. So lurking variables are those variables which are not taken into consideration or not mentioned, but they still might have an impact on the regression model. The next concept is causation versus association. Now, there is a difference between association and causation. Causation means a change in one causing a change in the other. Association is different. Association means that how the two entities are related to each other. Now, it is important to understand that linear regression is useful to quantify associations, but it is not a valid measure of causation. It can show you how a variable is associated with the other variable, but it is not a proper quantification of how one changes with the other, right? And finally, we get to the concept of collinearity or multicollinearity. Now, this problem occurs when my independent variables are heavily correlated with each other. So whenever we have two independent variables with heavy correlation with one another, then we need to drop one of them, otherwise they will cancel each other's effects. So the concept of so let me repeat the concept of collinearity or multicollinearity states that whenever two independent variables are heavily correlated, taking both of them will not be useful as they will cancel out the effect of one another. So guys, these were some of the basic concepts that we had to look in regression diagnostics. Thank you so much for listening. I'll see all of you all in the next session with a new topic. Thank you.